In this lecture, I will explain single hidden layer neural networks. That is, we will see the architectures of neural networks with a single hidden layer. We will get an understanding of the advantage of using hidden layers, and by this, getting a better idea of the concept of representation learning. And in the end, we will see some typical activation functions.
So we have just seen that an artificial neuron is just a graphical way of representing simple functions like logistic or linear regression. So if it's the same as linear or logistic regression, why is it useful? Of course, neurons are just the building blocks of neural networks. So we can compose them to networks, and these networks can represent more complicated functions. In fact, neural networks can represent extremely complex hypothesis spaces. And interestingly, it appears that they define very good hypothesis spaces in the sense that they are allowed to form good models for the prediction tasks and data occurring in this universe. What do you think? Can a single neuron build a model for binary classification to distinguish the red from the blue points? Maybe you can pause the video here and think a bit about an answer before continuing. A single neuron is restricted to only linear decision boundaries. Because of that, it cannot solve the following task. It could only make a decision boundary like that or that, but it's clear that it's hard to separate the blue from the red point by that. However, if we would perform some kind of coordinate transformation, this could look very differently. For example, we could transform the Cartesian to the polar coordinates. For a brief recall of the polar coordinates, if this is point 0, the polar coordinates of a point would be given by the angle here and the length of this vector. It's called radius. If we transform the blue and red points to this polar coordinates, this would look like shown in this picture below. And clearly here we could use a linear classifier. Therefore, instead of performing a linear classification in the original space where it doesn't work, we could first transform the old presentation to a new presentation and perform a linear classification there. Analogously, instead of using a single neuron, we could use a more complex network. That is, instead of having this single neuron here, we would have a network where the input neurons are transformed to some new representation which is given by the output of some so-called hidden neurons, and those are then forming the input to an output neuron. Generally, it is very critical what kind of features we feed into a classifier, because this really depends on if the classifier can solve the problem or not. Before the age of deep learning, features were often designed by hand by some domain experts. So when images or, for example, speech should be represented, people designed handcrafted features for this kind of data. This step of the machine learning pipeline is called feature engineering. And as the name says, there's some engineer really designing the features. Deep learning, however, works without feature engineering. And this is because it can learn the features automatically by itself. This is what we refer to as representation learning. So, how does a single hidden layer neural network look like? First, recall that each single neuron consists out of two steps. First, the weighted sum of inputs plus the bias, that is the affine transformation, and then an activation, which is usually a nonlinear transformation on the weighted sum calculated in the step before. Then in single hidden layer networks we have two layers of neurons where we don't count the input layer. First we have a hidden layer which consists out of a set of neurons, and then we have the output layer which consists out of one or several neurons. Multiple inputs are then simultaneously fed into the network, and we compute the output of the hidden neurons in the hidden layer by performing the two-step computation. First the affine transformation, then applying the activation function in each of the neurons. Given the output of these hidden neurons, these are fed into the output layer, where again first affine transformation is applied and then an activation function is applied to the weighted sum. Let's look at this in more detail now by looking at this small example of a neural network with one hidden layer where we have 3 neurons in the input, 4 neurons in the hidden, and 1 neuron in the output layer. First, let's assume that we have given some input given by -3, 1, and 5. Now we assume that this network is already trained and that we already know the weights of the networks. How we train that and how we get these weights in the end will we learn in later lectures. For now they are just given. Now the input to the first hidden neuron here would be calculated as follows. We would multiply the first input with a weight 1, 1, which connects the first input neuron to the first hidden neuron. This would be -3 times 3 in this case. Then we would multiply the second input with the weight W21, which connects the second input neuron to the first hidden neuron, which would be -9 times 1 in this case. And then we would add the third input multiplied by the weight 3, 1, which connects the third input to the first hidden neuron. If we sum this up, we have 3 times -3, -9 times 1, 2 times 5, plus 5. This is -3. So this -3 is the input of the first hidden neuron. Okay, we continue the same pattern for all the inputs of hidden neurons. The second one, the third one, and the fourth one. You can go through that step by step to see that all the calculations are done exactly the same way as we calculated the input of the first hidden neuron. So we got the inputs of all the hidden neurons, -3, 2, 0, and 7. And then apply the activation function, which in this example is the sigmoid, to these values. This gives us the values 0.05, 0.88, 0.50, and 0.99. In the next step, we feed these values that we just calculated into the hidden neuron and weight each with the weight associated to the connection of the hidden neuron to the output neuron. We again have weighted sum and a bias term of the output neuron. By that we calculate the input of the output neuron, which is given by 0.57 if you do the calculations. And then again the activation function of the output neuron, which again is a sigmoid in this example, is applied, giving us the final output 0.64 of the neural network. Now you can wonder what happens if you don't use a nonlinear activation function in the hidden neurons, but a linear function instead. In that case, the neural network can only learn linear decision boundaries. So we don't gain anything from using this additional hidden layer. That this is indeed true, that we can only learn the linear decision boundaries, is quite easy to show, and you could try to do that as an homework. There are very different choices of activation functions, which are, as said, usually nonlinear, but we will see different in the course of the lecture and see two typical examples now. One very popular choice nowadays is the so-called ReLU function, the rectified linear unit, which is just such a function which is 0 on the negative x for negative x and the identity for positive. So it's a max of 0 and y. Another choice is a sigmoid function, which is such a nonlinearity which approximates 0 when going negative and approximate 1 when on the positive side.